In this video, we will discuss basics of hypothesis testing. In statistics, a hypothesis is a claim or statement about a property of a population. A hypothesis test, or test of significance, is a procedure for testing a claim about a property of a population. The property of a population referred to in the preceding definitions is often the value of a population parameter. So here are some examples of typical hypotheses or claims. Mu is less than 98.6 degrees Fahrenheit. The mean body temperature of humans is less than 98.6 degrees Fahrenheit. P is greater than 0.5. The proportion of consumers not comfortable with drone deliveries is greater than 0.5. Sigma equals 15. The population of college students has IQ scores with a standard deviation equal to 15. Consider the claim that the majority of consumers are not comfortable with drone deliveries. Using P to denote the proportion of consumers not comfortable with drone deliveries, the majority claim is equivalent to the claim that the proportion is greater than half, or P is greater than 0.5. The expression P is greater than 0.5 is the symbolic form of the original claim. In this example, we have the claim that the population proportion P is such that P is greater than 0.5. Among 1,009 consumers, how many do we need to get a significantly high number who are not comfortable with drone delivery? A result of 506, or 50.1%, is just barely more than half. So 506 is clearly not significantly high. A result of 1,006, or 99.7%, is clearly significantly high. But what about the result of 545, or 54.0%, that was actually obtained in a survey by Pitney Bowes? Is 545 significantly high? The method of hypothesis testing allows us to answer that key question. It's easy to obtain hypothesis testing results using technology. The screen displays on page 359 of the textbook show results from 4 different technologies, so we can use computers or calculators to do all of the computational heavy lifting. Examining the screen displays, we see some common elements. First, they all display a test statistic of z equals 2.55 when rounded. And second, they all include a p-value of 0.005 when rounded. These 2 results are important, but understanding the hypothesis testing procedures is critically important. Focus on understanding how the hypothesis testing procedure works and learn the associated terminology. Then the results from technology will make sense. Hypothesis tests are also called tests of significance. In Chapter 4, we used probabilities to determine when sample results were significantly low or significantly high. This chapter formalizes those concepts in a unified procedure that is used often throughout many fields of application. There is a flowchart on page 360 of the textbook that is too big to replicate here, but it summarizes the procedures used in 2 slightly different methods for conducting a formal hypothesis test. We will proceed to conduct a formal test of the claim from our last example that P is greater than 0.5. In testing that claim, we will use the sample data from the survey cited with X equals 545 customers not comfortable with drone delivery among N equals 1,009 customers surveyed. The objective of the first 3 steps of hypothesis testing is to identify the null hypothesis and alternative hypothesis so that the formal hypothesis test includes these standard components that are often used in many different disciplines. The null hypothesis includes the working assumption for the purposes of conducting the test. The null hypothesis, denoted H0, is a statement that the value of a population parameter, such as proportion, mean, or standard deviation, is equal to some claimed value. The alternative hypothesis, denoted H1, HA, or H capital A, is a statement that the parameter has a value that somehow differs from the null hypothesis. For the methods of this chapter, the symbiotic form of the alternative hypothesis must use one of these symbols, less than, greater than, or not equal to. The term null is used to indicate no change or no effect or no difference. We conduct the hypothesis test by assuming that the parameter is equal to some specified value so that we can work with a single distribution having a specific value. Here is an example of a null hypothesis involving a proportion, H0, P equals 0.5. Here are different examples of alternative hypotheses involving proportions. H1, P is greater than 5, H1, P is less than 0.5, or H1, P is not equal to 0.5. Here are the first three steps of hypothesis testing. First, identify the claim. Identify the claim to be tested and express it in symbolic form. Second, give symbolic form. Give the symbolic form that must be true when the original claim is false. Third, identify null and alternative hypotheses. Consider the two symbolic expressions obtained so far. The alternative hypothesis H1 is the one not containing equality, so H1 uses the symbol greater than or less than or not equal to. The null hypothesis H0 is the symbolic expression that the parameter equals the fixed value being considered. Given the claim from our example that the majority of consumers are uncomfortable with drone delivery, we can apply steps 1, 2, and 3 as follows. Step 1, using P to denote the probability of selecting a consumer uncomfortable with drone delivery, the claim that the majority is uncomfortable with drone delivery can be expressed in symbolic form as P is greater than 0.5. Step 2, if the original claim of P is greater than 0.5 is false, then P is less than or equal to 0.5 must be true. With the p-value method of testing hypotheses, we make a decision by comparing the p-value to the significance level. In a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. To find the p-value, first find the area beyond the test statistic, then use the procedure summarized below. If the critical value is in the left tail, the p-value is equal to the area to the left of the test statistic. If the critical value is in the right tail, the p-value is equal to the area to the right of the test statistic. And if the critical value is in two tails, the p-value is equal to twice the area in the tail beyond the test statistic. For example, using the data from the last example, the test statistic is z equals 2.55, and it has a normal distribution area of 0.0054 to its right. So a right-tailed test with test statistic z equals 2.55 has a p-value of 0.0054. Step 3. This step has two parts. Identify the null hypothesis and the alternative hypothesis. Identify H1. Using the two symbolic expressions, the alternative hypothesis is the one that does not contain equality p greater than 0.5. We get H1 is p is greater than 0.5. Identify H0. The null hypothesis states that the parameter is equal to the fixed value being considered. So we get H0 is p is equal to 0.5. If you are conducting a study and want to use a hypothesis test to support your claim must be worded so that it becomes the alternative hypothesis and can be expressed using only the symbols less than, greater than, or not equal to. You can never support a claim that a parameter is equal to a specified value. Here is step 4 of the procedure. Select the significance level. Select the significance level alpha based on the seriousness of a type 1 error. Make alpha small if the consequences of rejecting a true H0 are severe. The values of 0.05 and 0.01 are very common. The significance level alpha for a hypothesis test is the probability value used as the cutoff for determining when sample evidence constitutes significant evidence against the null hypothesis. By its nature, the significance level alpha is the probability of mistakenly rejecting the null hypothesis when it is true. The significance level alpha is equal to p, the probability of rejecting H naught when H naught is true. The significance level alpha is the same alpha introduced in the last chapter where we defined critical value. Common choices for alpha are 0.05, 0.01, and 0.10. 0.05 is the most common. Here is step 5 for the procedure. Identify the test statistic that is relevant to the test and determine its sampling distribution, such as normal, t, or chi-square. To determine which distribution to use, recall that we learned in chapter 7. If we are looking for a proportion p or a mean mu, and we know the associated standard deviation, use the normal distribution z. If we are looking for a mean mu and do not know the associated standard deviation, use the student t distribution. If we are looking for the standard deviation or variance, use the chi-square distribution. Steps 6 and 7 depend on the testing method that we use, the p-value method or the critical value method. We start by introducing concepts common to both methods. The test statistic is a value used in making a decision about the null hypothesis. It is found by converting the sample statistic, such as p hat, x bar, or s, to a score, such as z, t, or chi-squared, with the assumption that the null hypothesis is true. The test statistics used in this chapter appear here. Z equals p hat minus p over the square root of pq over n. T is equal to x bar minus mu over s divided by the square root of n, and chi-square is equal to n minus 1 times s squared over sigma squared. From the last example, we have a claim made about the population proportion p. We have n equals 1009 and x equals 545. So p hat equals x over n, which is 0.540. With the null hypothesis of H naught, p equals 0.5. We are working with the assumption that p equals 0.5, and it follows that q equals 1 minus p, which is 0.5. We can evaluate the test statistic as shown below, or use technology to find a more accurate value. Z equals p hat minus p over the square root of pq over n, which is equal to 0.520 minus 0.5 over the square root of 0.5 times 0.5 over 1009, which is equal to 2.54. The critical region, or rejection region, is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. Depending on the claim being tested, the critical region could be in the two extreme tails, it could be in the left tail, or it could be in the right tail. In a two-tailed test, the critical region is in the two extreme tails, regions under the curve. In a left-tailed test, the critical region is in the extreme left region, or tail, under the curve. And in a right-tailed test, the critical region is in the extreme right region, or tail, under the curve. Hint: look at the symbol used in the alternative hypothesis H naught. The symbol greater than points to the right, and the test is right-tailed. The symbol less than points to the left, and the test is left-tailed. The symbol not equal to is used for a two-tailed test. We'll pause here and continue in the next video.